In the last video, we went through the Ret2Win challenge, where we overflowed the buffer in a program to redirect the execution to a function of our choice. So, a function called win, in our case it was called hacked, but that's the general idea. This time around, we're going to do something very similar, but we're going to look at a program which takes in parameters as a function and see can we jump to that function while setting the parameters that go with it. This is the first time that we'll look at a 32-bit and a 64-bit binary because there's some quite big differences between how these are processed. Okay, so let's jump into it. I'm not going to do the compiling this time around, but everything's compiled the same way. We don't have any protections. And let's check the file type first of all. Same as last time, 32-bit LSB executable, dynamically linked, not stripped. We'll have a look at the protections. And we don't have any protections in place. So we'll not worry about what these are doing just yet. Let's go ahead and try to run the program first of all. We can try to overflow the buffer, we get our segmentation fault, and we basically need to go and have a look at the code, or at least have a look at the assembly or decompiled code to try and work out what we need to do here. So I'm going to open up the code first of all. Remember, we won't always have access to code, but we'll be looking at the code in Ghidra and in GDB as well, so we'll just also go and have a look what the actual C code is. So this is almost identical to our previous challenge, where we had the main function, it's calling register name. It has a 16-byte buffer and it's going to read in our name without checking to make sure it fits in this buffer. We've got this hacked function which is never actually called, so our goal is going to be to redirect the execution from the register name function to this hacked function. The only difference is this time this hacked function takes in a first parameter and a second parameter, both int, and it's going to check to make sure those parameters equal what they should equal before it either tells us we've accessed a secret function or tells us we're not authorized. Let's just open this up in Ghidra as well. We'll do the Ghidra auto Ret2Win. Just going to see what it looks like compared to the source code. We go into our functions. Again, we'll go into main. We'll have a look at this register name function. We might want to go and start renaming stuff like our buffer. And what's important here is obviously the hacked function. We want to have a look at that and see how it's different. So again, we can right click and convert these to the different formats, or we can just go and have a look in the assembly code on the left. We'll see it's actually here as code babe, and it was dead beef here, but we just converted it as well. Let me convert that back. And the important thing to notice here is that we have the comparison being done, so it's actually comparing what we have on the stack. If we see up here, the param1 and param2 are on the stack, and we're checking EBP plus the offset of that parameter and comparing it to the literal value dead beef, and then the same with code babe. So that's what's happening over here. It's reading our parameters off the stack and then it's comparing them. So that's just important to remember because it's going to be very different when we get over to the 64-bit, which uses registers rather than reading the parameters off of the stack. That's about it. Let's go and try to exploit this manually, and we'll go and have a look at it with GDB as well. Actually, let's open up GDB-PwnDbg first, because I just realized we should go and find out what the offset is. So remember we did that cyclic 100 pattern last time. You can do cyclic whatever, let's do cyclic 200. We get 200 bytes, and we're going to go find out how many of these bytes do we need to overwrite the return address, and then we'll know what offset of how much padding or junk that we need to put before we put the return address in our payload. So we'll run the program, paste that in. We've overflowed the buffer. We've got the same characters that we had in last time, HAAAA. So the code is very similar to our previous example. We'll do cyclic-L, paste that in to look it up, and we'll see that it's 28 bytes that we need to overwrite. So just to visualize this, let's go and put together another Python payload. We'll do Python 2-C, and I'm going to do print a times 28, so that's enough to overflow the buffer and get up to the return address. And then let's put in the address of that hacked function. So I'm going to get disassemble hacked. You can get this from Ghidra or something if you want. And this is the address we need to put in little endian format. So paste this in here so I can see what I'm doing. And \x 82 \x 91 \x 04. And we need some padding on that last one. So \x, you can't just do 8, we need 08. And let's get rid of this bit. And let's set up some parameters. Now one thing to bear in mind here is that we also have the return pointer on the stack first. So what I'm going to do is the return pointer, let's say, is AAAA, And then we've got our parameters. So our parameters, let's say BBBBB plus CCCC. Print that out. Again, we need to send this to a payload file because the memory address isn't printable in ASCII. So we'll do that again, send it to payload, and let's go and test it out. So I'm going to set up a breakpoint again for that return address. Let's disassemble the register name function, and let's get the return address down here. Let's break at that address, and we're going to run a program. We're going to send in that payload. We hit the breakpoint, so it's just about to return from register name, and it should be returning back to the main function. Remember that the main function called register name, so it should go through this code and then return to the main function. But in this case, we overflowed the buffer with this address, so it's going to return to the hacked function. And we can also see, if we look down here, that we have the comparison right here between the first parameter, which should be dead beef. Where is it? Dead beef, and the second one should be code babe. We can see that comparison down here as well. So let's just step through. We could set up breakpoints here as well to make things a bit quicker, but I'm just going to step through until we get down to that first comparison. And you can see here we've got the first comparison. We can actually go and have a look to see, so we've got dead beef in here at the moment, which is what we're comparing it to, and we're comparing it to this EBP plus 8. So let's print that out as hex. And we've got 424242. So that is the B's. Let's go back. Let's have a look at that again. So we had the return pointer. We don't need to worry about that. We just needed to pad that out with anything. So we could have literally just typed in here junk, just as long as we have something to pad up to where our first parameter should be. Then we have those B's, which is 42424242 in hex. And then the next parameter should be the C's. So the only thing is, if we hit next now, you see we've got a jump not equal. So it's saying if dead beef does not equal whatever is found at this address here, which it clearly doesn't, then it's going to jump down to hacked 57, which means it's never actually going to check to see if the other parameter matches. Let's hit next. You can see here, jump not equal, we've got a little tick. Next again, and it's jumped, so it's not actually going to compare the other parameter. We get unauthorized. So just to be clear what happened there, we reached the function and it checked to see if this first parameter matched, and because it didn't, it doesn't even bother to test the second one because it knows that there's no way we're ever going to execute this code because we need both of these parameters to match in order to do that. So let's go and change the payload slightly. I'm going to go change this one to what it should be. So \xde, \xad, \xbe, \xef. Send it to a payload, and now we've got junk here as well. It doesn't matter. Let's run this again with that payload. And we're going to hit the same breakpoint. See, we can see this junk now, which is our return pointer. We can see dead beef is our next parameter. And then we can see those C's where the code babe should be. So let's hit next, 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 next. We get down to this comparison with dead beef. And again, we can go and have a look to see what's in this location. So we're printing out as hex the EBP plus 8, dead beef. So that one matches. So this time, if we hit next, we get to this jump not equal, and it didn't. These two did equal, so it's not going to jump down to hacked 57. Instead, it's now going to compare code babe to whatever is that EBP plus 0xc, which is 12 in decimal. Which makes sense, right? Because we have our EBP plus 8, and we had a 4-byte variable. We had, as we can see here, these 4 bytes. So 4 bytes after 8 is 12, and that's our next value on the stack. So again, let me take a copy of that. X, print that out. It's obviously 43434343 because we put in all C's, which means if we hit next, it's going to say jump not equal because they didn't equal, and it's going to, if we hit continue, it's going to tell us we're not authorized. Oh, we actually got invalid address there, that's fine. So we did actually get not authorized. If you look up here, we got not authorized, but then we got a seg fault, which is why it crashed afterwards. This time, let's actually fix this so it does work. Let's change this to codebabe \xco oh, let me go back, \xde \xba \xbe. Send that to the payload, and let's run this one more time. Run payload. Alright, so we're going to hit our breakpoint. Let's go down to that first comparison. It's good just to get used to this, just stepping through code and trying to see what's actually happening and what's in the registers as it happens. We've got our first check, so we know this is dead beef. We can see it right here on the stack. We can see code babe afterwards, so we can just hit next. Jump not equal wasn't true, so these two did equal. Next. And oops, I just skipped the code babe one, but that also was fine, so it didn't hit jump not equal. So if we hit continue now, we're going to get that segmentation fault, but if we just scroll up to see what actually happened, we did get that message to say, this function is top secret, how did you get in here? So we don't need GDB to test that now, we can now just run the program and pass in that payload. And that's how we exploit it manually. Let's go and have a look at our first PwnTools script, exploit.py. Again, as I mentioned in the last video, this is just a lot of stuff you don't really need to touch. Actually, this has changed a little bit since the last video. So in the last video we had the start function to easily swap between debugging, remote and local. We had our GDB script in case we want to debug it directly from PwnTools. And we have our binary and context and login and stuff set up here. The only difference is, in the last example, in the second script that I showed, we had some code to find out the offset for us. So this is just some code to automate that. And instead of typing in 28 as our offset, it's going to find that for us. So we didn't actually need to do any of that in GDB. We can just do it automatically with PwnTools. It's going to launch the program, it's going to send a payload, it's going to wait for it to crash, and then it's going to have a look in the core dump to see where were the 4 bytes that we entered from that cyclic pattern, and then it's going to return the instruction pointer offset. The only thing to mention, it's slightly different for 86 or for 32-bit and 64-bit, so you might need to comment out or uncomment a line depending what you have here. And the important stuff is all down here where we have exploit goes here. We have a payload being set up here. We have offset is set as the index. So basically this is going to generate 28 of the cyclic pattern, 28 bytes. And then after the 28 bytes, it's going to send this list of stuff. And the list of stuff starts with the hacked function address, which again we don't need to specify because we've specified the binary. It can go and find that for us. And then the return pointer where we just had junk last time, but you can put whatever you want here. I've just done 0x0, just something to pad it out. Then we've got our first parameter and our second parameter. It's going to flatten all that for us. It's going to write the payload to a file and we're going to send it off. So not too much else to mention there. Let's try and run it. We get lots of output because we've got debug mode on, and we can see what it's doing here. It's parsing the core dump. It's trying to work out how many bytes, and it's worked out 28. And then it's sending off the exploit. So the exploit, you can see here, it's got 28 bytes from the cyclic pattern, these A, B, etc. And then it has the return address of the function. It has our padding for the return pointer, and then it has dead beef and code babe as our parameters. And then we get our top secret function access. Like the last video, we're going to have a look at this ROP script. So quite often I'll create a manual script, an auto script, and then a ROP script. Each one has a bit more automation than the previous. You can see in this case what's different is we have this ROP object being created here. Let me highlight that. So this is a class which simplifies the generation of ROP chains. So we can tell it we want to call hacked, and these are the parameters we want to pass, and it'll build up the payload for us. We just send that off as the ROP chain. So this is the only bit of code that's different here. As you can see, instead of building up the payload manually, we're letting it do the hard work for us. And if we want to, we can do rop.dump to print that out. Sorry, I think we need to... I can't remember, do we need to pretty print that or not? Let's have a look. Python ROP and it runs through. You can see it's basically going to put together the payload for us. You can see here the rop.dump that we just called, and it's found the function address. It's put in here as the return address, just some random junk from that cyclic pattern, and then it's also populated the arguments on the stack as well. And again, you can have a look here. If you're ever having a lot of problems with the payload, try and do it with some automatic functionality in PwnTools, and then have a look through what's actually in the payload. It's a good way to debug your manual payloads. Now we're going to move on to the 64-bit edition or version, and we'll just do the same stuff here. Let's run file. It's compiled with all the same options but without the -M32 option, so it's 64-bit instead. We can verify with checksec to make sure we don't have any additional protections, and we don't. we could open this up in Ghidra as well. Let me import it. Oh, destination file name already exists. Okay, so we need to actually close this one down to import it. Alright, I'm not going to bother importing it. We've had a look at this in Ghidra for the 32-bit. We'll just have a look at the source code for this one and have a look at it in GDB as well. So let's open up the source code first of all, see what's different. And it's very similar. We've got all the same code down here. The only difference is we're bringing in a long instead of an int. And you can see here we have basically these 64-bit parameters instead. And the parameters are just duplicated, so it's just the same thing repeated twice. But if we're going to have a look at this in GDB, things are going to look a bit different. Let's open up GDB-PwnDbg, Ret2Win params. We can have a look, info functions, disassemble our hacked function. And let's get up the 32-bit just to compare it, so we'll disassemble hacked here as well. And the main thing that we'll notice is that the dead beef was on the stack. Remember, it was EBP plus 8, and then CodeBabe was on the stack EBP plus 12. If we have a look at the 64-bit edition, it's actually using these registers instead. So the registers are RDI, RSI, RDX in that order. So the first parameter that's being passed to a function will be from the RDI register, and the second parameter will be in the RSI. And then you can see it's taking the literal values to the RAX. It's going to compare that to the value that we've placed on the stack from the RDI. And then it's going to do the same thing with CodeBabe. It's going to copy the value from the stack, which we moved from the RSI onto the stack. And it's going to compare that with CodeBabe. Note that these brackets are used to represent when these are pointers as well. So you can either have a value in a location, like a literal value, or you can have an address of where the value is stored, so a pointer to the value. So that's what you see in there. But essentially, it means we're going to need to populate these registers. We can't just send in the return address of hacked followed by the parameters. We need to send the return address of hacked, and then we need to put those parameters into these registers. And in order to do that, we need to find some ROP gadgets. So let's take a look at that. I'm just going to find out how many bytes we need here as well to overflow the buffer. So let's do our cyclic 100. Let's take a copy of that pattern. Let's run the program, paste that in. And the other thing to mention here, because it's 64-bit, you can see all the registers are different. Instead of an EIP, we have an RIP. Instead of an ESP, we have an RSP. And notice that instead of 4 bytes being in these registers, we have 8 bytes because it's 64 bits instead of 32 bits. The other thing to notice is that we would expect these bytes to have ended up in the RIP, but they didn't. And it's just the way 64-bit works. If you try to give it an invalid memory address, it won't even populate the RIP. So what we need to do in this case is take the values that we have from the RSP. So I'm going to take a copy of the GAAAA. That's what would have made it into the RIP. You can take a copy of the 8 bytes or just the 4 bytes, it really doesn't matter. Because we only need to see where it starts, we don't need to know the length. And we can do again cyclic-L, paste that in, and we find out it's 24 bytes this time instead of 28 bytes. Okay, so what I'm going to do is open up Sublime and just kind of talk through our plan of action here. Let's say our padding, which is the 24 bytes. So, okay, let's put together our Python command at the same time. We'll do Python C, Python 2-C, and we'll print a times 24 plus. So that's our padding, which is right here. And the padding is going to be followed by the function. So we've got our hacked function, where we're going to put the address here. So let's put this in little endian format. Grab that from GDB. Disassemble hacked. Grab this address. Now bear in mind that this is also 64-bit. Using PwnTools, we won't need to worry about that, but we will need to worry about it doing it manually. So we can paste this in here. Basically, we need to do reverse order. And we need 5 of these 0 padded bytes. Okay, get rid of that. We have now, let me zoom out of this a bit so we can actually see the whole thing. Alright, so we've now got our 24 bytes of padding and then our return address of the hacked function. What's next? We know that we're going to need to put our dead beef value up there. I'm going to add this now. Let's do \xde xad /xbe /xef, and this time along around we need 2 of them, so just duplicate that. But remember, we don't just put this straight on the stack, so what we want is we want for this to be popped into the RDI register, and that'll be used as a first parameter. So before we provide that, what we need is a gadget to do that. So let's put this together up here. So padding, return address of hacked, and then pop RDI plus param1, and then the second parameter we want to pop into the RSI, which is where it'll be read from, and then param2. And that's it, that's all we need to do here. But we need to go and find this pop RDI gadget. So we'll use Ropper to do that. You can find this in GDB or in Ghidra, but Ropper's a handy tool to do this with. So we can say Ropper -- file and then just pass in the binary, and it'll give us all of these ROP gadgets and the addresses of them. In our case, we're looking for pop RDI, so I'm actually going to add a search and say pop RDI. And here's the address of a pop RDI return instruction. So that's it, we just need to take this address. We're going to need to pad it out again though. Right here, our pop RDI will be this address, so /x4b /x12 /x40, and then again we need 5 bytes of padding. And that's our pop RDI. So again, it's going to jump to our hacked function. The next instruction it's going to call is pop RDI, which is going to pop the next thing in the stack into the RDI register. So the next thing we want is our pop RSI and second parameter. So we'll put that there as a space for our pop RSI, and let's do our cafe babe. No wait, it's code babe, is it? I can't remember it now. Code babe. So CO, and then we'll go back DE /x /x BA /x BE. I never get used to writing these in reverse order. Alright, so there we go, there's our 2 parameters. We need to find this pop RSI now, so let's go back to Ropper. Let's search the same thing, but this time pop RSI. And we don't have a pop RSI gadget, so we've got this instead, which is pop RSI, then pop to R15, and then return. Which means if we have these values on the stack, we put our pop RSI here, then the first value is going to go into the RSI, but then we need another value on the stack to go into the R15, so we would just put in some junk there for that. And I've just realized one glaringly big mistake in our process here. So actually, we're calling the hacked function before we're setting up the parameters. So let's change that around. Obviously, we need to first make sure that the registers have the parameters in place, and then the last thing we'll do is call the function. So instead of overflowing the return address with the address of the hacked function, we're going to overflow it with the pop RDI gadget to pop the first parameter into the RDI. We're then going to execute the pop RSI R15 gadget to pop param2 into the RSI and junk into R15. And then with all the parameters in place, we're going to call hacked. Sorry about that. I'm sure some people were screaming at their screen. What are you doing? But there we go. Alright, so we've just changed that around. So now it's pop RDI, our first parameter, and now we need our pop RSI. Let's grab that gadget address. So /x49 /x12 /x40, and let's get these zeros as well. And then we need our junk as well, because obviously if we have, as things currently stand, it's going to pop the second parameter into the RSI, and then it's going to pop our hacked function address into the R15, which is not what we want. So we need some padding here. I'm just going to make it all zeros. Just add that here. Another 3 of those. And I think that's looking pretty good now. Let's try it out and see what happens. So we'll just print this again. Again, we're not going to be able to copy and paste that. Let's send it to a file called payload. And let's run the program and pass in payload. Oh, I think I'm in GDB again. Where's the program? Ret2Win, payload. We run it and we get this function is top secret. How did you get in here? So if we went and changed something, let's change, say, let me change this Cafe Babe slightly. We'll change it to something else, BD, and send that again. And let's run the program. This time we did call the secret function, but we got that other message to say unauthorized access because we have several conditions we need to meet. We need to overwrite the return address with our hacked function, but we also need to make sure these parameters are as expected. Okay, that's how we exploit that manually anyway. I hope that was okay. I know it's a little bit confusing getting used to the differences between 32-bit and 64-bit. Not really the address length, that's probably not too difficult, but it's quite a different format in terms of having to pop parameters into these registers in order for functions to be called. Let's go and take a look at how we can do this in PwnTools as well. So we've got exploit.py again, let's have a look at that. And this is basically the same. The only thing I've changed up here is the 64-bit. Remember I said that this find instruction pointer function is slightly different depending whether it's 64-bit or 32-bit, so you just need to go and comment out a line depending on what architecture you're working with. Apart from that, all this stuff's the same apart from the file name, and because we have the context.binary set up here, it knows what architecture and whether it's little endian or big endian, things like that. It means we don't need to say 000 etc. here with the padding. It's going to know that this isn't a 32-bit address, it's a 64-bit address, and it knows that because it's looking at the binary and working that out. So we've basically put in the addresses of our pop RDI gadgets and the same with the RSI. You don't need to do this with Ropper and set it manually, you can do it with PwnTools and I'll show how to do that shortly as well. And then we build up our payload. So again, at the offset that's identified, we're going to send in this list of stuff. The first thing is going to be the address of the pop RDI instruction, and it's going to pop this value into the RDI register. That's our first parameter. The next instruction is going to pop the first value here into the RSI, which is our second parameter, and the next value into the R15, which is just junk, because we couldn't find a pop RSI gadget. And then finally, with everything in place, we're just going to call the hacked function. We're going to write the payload to a file so we can run it again in future, and we're going to send it off to get our flag. Or not our flag, but just to accomplish our goal anyway. So let's try it out. We run through that, we get, as expected, this function is top secret. How did you get in here? And again, we can see everything that's sent off. We can see that we've got our, how many bytes of padding was it? Let's have a look. It was 24. So we've got our 24 bytes of padding, and that's followed by the pop RDI address, and then our first parameter. That's followed by the pop RSI R15 address, and our second parameter, and some junk for the R15, and then finally our hacked function address. If we don't want to see all of that stuff, we can go and change the log level here, so you can go and set this to info if you don't want so much output. But I typically like to see what's going on in the background. There's still quite a bit of output there. You can also change this, I guess, to warning, and then you'll get pretty much nothing. Okay, so finally, let's have a look at our ROP script, where we automate this through ROP Objects. So again, all this is the same as the last script we're looking at. The difference is we are using the ROP library to just call the hacked function and pass in these parameters. So let me do that pretty print rop.dump again, just so we can see what's actually happening. And again, the payload is literally just sending this off. So we'll try to run that. We get back our top secret function, and we can go and have a look at what it actually did for us. So whenever we called rop.hacked, what it's actually doing is it's going and assembling this whole payload for us. So it's finding the pop RDI gadget, which is this address here. It's popping our dead beef into the RDI. This is the decimal value, the integer. And then it's finding the pop RSI R15 gadget. It's going to pop code babe into the RSI, and then it's going to pop some junk into the R15. You can see it actually says pad R15, and then it's going to call the hacked function. So this is exactly what we did manually. We've just allowed PwnTools to do the hard work for us. So in this video, we expanded on the Ret2Win challenge that we looked at previously to call a function which has some parameters, and we also looked at how to do that with a 32-bit and a 64-bit application, which, as we've seen, is quite different. In the next video, we'll be looking at injecting shellcode. So let me just show again. If we do that checksec --file Ret2Win params, we have NX disabled, which basically means that whenever we're injecting that address of the hacked function, if there was no hacked function, what we could do instead is put the address of some shellcode that we inject, some malicious shellcode to do something like get a shell or to print out a flag or whatever you want to do really, and it's going to execute that. But if this NX was enabled, it would basically mean that data on the stack is either marked as data or executable, so you can't just inject code and expect it to execute. So we'll have a look at injecting some shellcode, and then after that we'll turn this NX disabled on, and then we'll see how we can bypass it. But I hope you've enjoyed this video anyway. If you have any questions or comments, leave them down below. Thanks.